Awesome, will do. Thanks, Tiffany.
Yeah. Okay.
All right. Yeah, so I'm really excited to be here today and tell you a bit about my PhD research. And so, as Tiffany mentioned, it has been mostly focused on thinking about future direct imaging observatories. And so, my talk today will be separated in two of my main PhD projects. So, the first section focuses on addressing planet detection confusion. And the second section is kind of looking back at solar system planets as exoplanet analogs. And I like to start off just by motivating my work a bit so we can all be on the same page in terms of the context. So, current direct imaging efforts are focused mostly in the infrared on young, giant, self luminous planets. And my work is specifically looking towards future missions. So, those that will enable reflected light observations of more mature planets down to solar system analogs. Some of those missions include the Roman Space Telescope, which will hopefully be able to enable reflected light observations of a couple of cool Jupiters. We'll also have the extremely large class of telescopes from the ground to assist in this endeavor. And then looking farther into the future, we'll have something like HWO to hopefully enable the detection and characterization of close-in planets on shorter period orbits. Now on this slide, I'm also showing you a couple of tables here just for some context. So on the top, I'm showing you the contrast requirements as well as the angular separation in a system at 10 parsecs for two solar system planets. So you can see for something like Earth, we really need contrast levels of better than 10 to the minus 10. And then for Jupiter, we're only about an order of magnitude better there. On the bottom table, what I'm showing you are some observing instruments, as well as their contrast requirements and their inner working angles. And this is all relative to the Gemini Planet Imager, which is a currently operational observatory from the ground. So you can see that moving to deeper and deeper contrast, we really are going to need something like HWO, where I have the Habex chronograph standing in here, to enable those detections of solar system analogs. Now, as we look to these future missions, we can be excited that they'll enable access to new regimes of exoplanets and new science. But of course, they will also bring new challenges that we need to be ready to address when these observatories are on sky. So I'm emphasizing some of those points here with a plot from the Habex final report on the right, where you're seeing simulated detections of a three-planet system around a sun-like star. This is a system that's been imaged 4 times spread out over a year. And if you look at these images closely, you can see that there is some orbital motion between the planets in the images. So of course, these advances in technology will be exciting to enable these types of detections, but they will also complicate the task of deciding when to observe a system for several reasons. The first of those is that being able to detect these planets orbiting closer to their star means that there might be more planets per image. And these shorter orbital periods mean that these planets will be moving between images and they also might not appear in each of our observations. That could be due to several different reasons, including potentially being blocked by their host star. Maybe they're blocked by our working angles of our instruments, or perhaps they're just too dark or too dim to detect based on their orbital phase. We also have that potential for false positive detections due to speckles or post-processing techniques. And then finally, as we're reaching down to these kind of new regimes of smaller planets, we also might lack precursor observations for the system, so we won't necessarily know what to expect. The final point that I want to make in my introduction here is that exoplanets can also only ever be imaged at partial phase angles. And I'm emphasizing this with a couple of currently observed systems. So on the left, we have Beta Pic with its planet B in a relatively edge-on orientation. So we would only catch those kind of outer near quadrature phase angles. And then something like HR 8799, where we have those planets orbiting in a more face-on orientation, we won't have that orbital phase variation, but it will only ever be a partial phase angle that we're seeing. So this leads me to part one of my talk, which has been focused on understanding how we can use photometry to support orbit deconfusion. So in this section, we will try to answer a couple of questions, including how confusion will affect future direct imaging observations, and also how photometry can help support deconfusion. So just to introduce the confusion problem for those who aren't familiar, some previous work has predicted that we might encounter this confusion problem when multiple planets are detected around a star over several observation epochs, and it's not clear which detection belongs to which planet. This figure is from a paper by my colleague Lena Begorliak, where you're seeing in the left-hand panel 3 detections of a 2-planet system. And then in the middle and right-hand panel, you can see that there are two very different ways that you can actually fit orbits to these observations. And so the issue here is that both of these orbit sets provide equally good fits to the data. And so we really need to consider some other methods on top of this relative astrometric information to decide which sets of orbits best fit the system. So my colleagues developed the deconfuser, which is an algorithm that was designed to rapidly assign detections to planets and to perform an assessment of this confusion problem. And just to kind of quickly walk you through the flow with this chart on the left here, what you give to the deconfuser is that relative astrometric information of those detections, so where the planets are on the sky compared to their host star. The deconfuser then performs a 3D grid search over the semi-major axis and then the x and y eccentricity vectors of the planet, and then fits the other three orbital parameters via least squares. However, this can still result in many possible orbit combinations, and so you need to decide which set of detections still belongs to each planet here. The deconfuser then finds the combinations that say best describe the detections by essentially ranking orbit options based on those that have the highest number of matched detections. So for example here, an orbit option which fits 2 out of 3 detections would be ranked lower than one that fits all 3. So at the end of this, what you essentially end up with is either one top ranked orbit fit for the system, or you can have a list of systems which are all equally ranked and fit the detections equally well. And so at this stage where you still have some system confusion, this is where we can essentially introduce another orbit ranking scheme, and we can further refine equally ranked orbits using metrics like photometric variation. And so my work has focused on augmenting this deconfuser with photometry to consider those changes in brightness between a planet's orbit and to assist in breaking ties between equally ranked orbits in the deconfuser. So to do this, I've developed a photometry model that calculates the expected phase angle of the planet given the orbital geometry determined by the deconfuser. So what you feed into the photometry model are those confused orbital parameters. And then with the phase angle, we can then calculate the phase function, that contrast ratio, and our expected photon count rate from the planet for each observation. This then gets us to a measured brightness for each detection. And so this is where we can bring in that actual orbit ranking scheme. And so with photometry, we can then provide scores to orbit options returned by the deconfuser in the form of a likelihood. And then we can compare the likelihoods of measured planet brightnesses for each set of orbits to rank orbits higher if they have a more statistically likely phase or brightness result. So I just want to kind of quickly walk you through how we take that output from the deconfuser and translate that into photometry. So from the deconfuser, we have our planet to star separation and our planet to observer separation. And so this is how we calculate our phase angle. With the phase angle, then we can feed that into some kind of phase function. So here we assume a Lambertian for simplicity. And then our phase function then feeds directly into calculating our planet flux density. So we assume some geometric albedo and planet radius. And then we feed that directly into an equation which considers the detector parameters. And so we can end up with our planet count rate at the detector. Now, once we have photometry, we can then calculate the likelihood of a given detection. So here I'm going to walk you through the steps that we take to actually get to this likelihood. The output of our noise model is essentially a probability density function, which describes the electrons that are read out by the detector. And here I'm representing that with a Poisson distribution. The actual output of the code is a combination of a Poisson distribution, a gamma distribution to model the gain from the EMCCD, and a Gaussian, which describes the read noise. The expected number of photons then, NP here, to be received at the detector depends on the number of photons reflected by the planet, of course. We saw that that is dependent on our phase angle, which comes from our orbital parameters. And then we also care about the detection time. So that's a parameter for our observing instrument, and then the background counts from the star. So each planet detection ultimately has a unique photon count due to the orbital parameters of the system. For each detection then, we end up with the probability of measuring a certain number of photons given those orbital parameters of the system, and this is described by our probability function here. We then need to consider each set of planet detections together to ultimately determine the likelihood of a given orbit match. So we assume that each detection here is an independent event, and then the likelihood of measuring all of the detections, given the parameters of the matched orbit, is the product of the individual detections. So this is our likelihood function here, where J is essentially your number of measurements. So then I can skip a few steps in the math here, and our probability distribution essentially follows the photon distribution plus the distributions caused by detector noise. We can plug in our expected number of photons from the planet to get our likelihood function. And then if we apply a natural log here at the end, we can also obtain the log likelihood function, which we could also use for ranking. Now here I just want to briefly walk you through a system example of ranking with photometry. So on the left-hand side, again, you're seeing some of those example detections. This time you're looking at 3 detections of a 3-planet system. And then in the middle and right-hand panel, you're again seeing those 2 confused orbit options that can be fit to these detections. Now, once we have these confused orbit options from the deconfuser, we can pass this through the photometry ranking scheme and compare option 1 to option 2 based on the phase variation. What we find here is that the likelihood of option 1, given the detections, is actually greater than the likelihood of option 2. And so where we started with this confused set of orbit options, with photometry, we can now disentangle these two. And because these are simulated systems, we can of course compare our orbit fits to what the true system parameters look like. And so the good news here is that we can see that option 1 is also the better choice for this actual simulated system. And we've tested this on a subset of highly confused systems with single band photometry. And what we see is that it supports deconfusion for 70% of confused systems across the board. Okay, so moving into part 2 of my talk, we're going to come back a bit closer to home to understand the ice giants as if they're as if they're exoplanet analogs. And just to briefly motivate this work a bit more, firstly, in the context of the solar system, of course, we know that Uranus and Neptune are not very well understood planets. And also that exoplanets of similar size are among the most commonly detected planets to date, which I'm illustrating here with the surface gravity versus bulk density plot. So you can see that the ice giant type planets in blue carve out a very distinct region of space compared to the gas giant like planets in orange, and even compared to these terrestrial sized planets where the moon and Mars have been plotted for reference. Now, to study the ice giants, at high phase angles, we have to use space missions because we're restricted to phase angles of about 2 to 3 degrees from Earth. We do have some previous observations from the Voyager missions. Of course, these are from the 1986 and 89 flybys. And while these were very scientifically useful and exciting observations, they left us with major questions about the differences between Uranus and Neptune, despite their relatively similar compositions. So the good news is that we have the New Horizons mission, which is now more than 61 AU from the sun. This is a mission that was launched in 2006, and you may be most familiar with it from its Pluto flyby in 2015. And now the New Horizons mission is at this very unique vantage point to essentially look back at the solar system and image the giant planets at high phase angles. So that's exactly what it did in 2023. There was a dedicated imaging campaign with the New Horizons multispectral visible imaging camera. And so in the left-hand table here, I'm showing you those observation details. And you can also see that we have one additional scan each from 2010 and 2019 of both planets. On the top right-hand side, I'm showing you the viewing geometry of the planets with respect to New Horizons. And then on the bottom right-hand side, you can see an example of what our observations actually look like. And so this is a subpanel of the images centered on Uranus and each of the 4 filters. And you can kind of make the analogy here of how these look a bit like what we would expect direct imaging observations to look like. And so for the rest of this, I'm going to focus on just the Uranus results. We published this paper at the end of last year. And the very unique feature of this work is that we also have simultaneous full phase observations of the planets. So on the left-hand panel, I'm showing you the Hubble observations. We're going from the bottom to the top. We move from bluer to redder wavelengths. And you can see that towards the infrared, that polar cloud feature starts to become more prominent as well for Uranus. We also have some complementary observations from ground-based community observers. This is thanks to a campaign organized by Susan Benecke. And so we also have longer baseline coverage of before, during, and after the New Horizons observations. Now, to handle this data, what we received from the team was essentially reduced data, but there were some striping artifacts that we needed to correct for, and we also had to actually identify the planet location in the images. Then we performed aperture photometry, and we converted those counts to a radiance factor or reflectance. And we do that following the equations that I've listed on the right-hand side of the slide here. These essentially account for the spatial scale of the observations, the specific filter transmission, and then you ultimately wind up with this reflectance value. Okay, so jumping into the Uranus results, what I'm showing you here is the reflectance, or that I over F, as a function of the sub-observer longitude. And we're going to focus just on the red filter, so those orange circles here, and the blue filter. These are where we had our highest signal. And what you can see here, firstly, is that we have no statistically significant rotational variation in our observations. And then also, when you take a look at those 2010 and 2019 points, there's no significant variation in brightness between time as well. Now, looking at the data in a slightly different way, we're looking at now the geometric albedo as a function of wavelength. So here we have the New Horizons points plotted from our observations, as well as what we predicted. Those are the square points here. And this is all in comparison to the empirically measured spectrum of Uranus from the ground, where we've scaled it by a Lambertian phase function to match the phase of the New Horizons observations. And so the main takeaway here is that, especially in the red filter, where we do have a good signal to noise, Uranus is actually dimmer than predicted by a Lambertian phase function. And so you might be wondering what this means in the context of exoplanets. And so here I've projected what that might look like in terms of contrast ratio if we roughly estimate Uranus at its current separation on the left-hand side, and then also arbitrarily scale it into about 6 AU on the right-hand side so we can increase that contrast here. And so you can see that something on the order of 10 to the minus 10 would be achievable by a mission like HWO. And to just emphasize a few points for exoplanets here, firstly, of course, we need to really understand the scattering in these near quadrature phase angle regimes so that we can, of course, understand the ice giants themselves within the solar system. These features can help us to constrain the energy balance of the planet from these multi-wavelength observations. But also, you're going to need these sophisticated phase functions to model atmospheric behavior of exoplanets and to accurately interpret our future observations. And then finally, fainter exoplanets may require more sensitive instruments or longer integration times for detection and characterization. So this is something that we really need to be aware of in advance of planning how to design our instruments and also planning to make those observations. Okay, and just before I summarize, I want to kind of briefly plug some of my additional work that I've been really excited about. Firstly, I'm clearly very interested in solar system analogs for exoplanet work. And so a project that I started last year with Alex Greenbaum at IPAC and Vanessa Bailey's team at JPL was to understand the feasibility of detecting a ring of some size around an exoplanet with the Roman chronograph. And so we're very motivated with this work by the increase in reflectance caused by Saturn's rings. And so we're hoping to better understand whether or not we could image a ring of some size with Roman in the future. And so I just want to point out that we're working on this. It's in progress work, and to keep an eye out for our paper in the future. And then also, as Tiffany mentioned at the beginning, I have also spent a lot of time working on maximizing the science return of ground-based exoplanet surveys. And so I've spent quite a bit of time recovering serendipitous detections of minor bodies from both ground-based and space-based telescopes. All right, so that brings me to my summary slide, which I will just leave up here, but I want to mention that the deconfusion work, we are currently finishing up the referee report for that initial study of single band photometry, so keep an eye out for the paper later this year. If you're interested in the Uranus paper, I have a QR code here that you're welcome to investigate in more detail. And otherwise, I'm happy to take questions.
All right, thanks so much, Sammy, for a great talk. Any questions? You can use either the hand raise tool or put something in the chat. Pick a question. Yeah, David, you already have a question. Go ahead.
Yeah, I may have missed this when you in your decomfuser, do you take into account the astrometric errors or doesn't?
Oh, good question. Yes, I didn't mention that.
Code.
So right now, the way that it fits orbits, we essentially, the astrometric error, we set a tolerance, which you can define based on whatever the user would like it to be. And so in the fits that we're running now, we set a tolerance of 0.05 arc seconds. Sorry, milliarc seconds.
Milliarc, yeah. Okay. Thank you very much. Great talk.
Thank you.
Vanessa, go ahead.
Yeah, really nice talk, Sammy. So I think I heard at the end of your decompuser section that you recovered the right solution 2/3 of the time or 7 3/4 of the time, roughly. Okay, I'm curious, were there any commonalities amongst the situations where it failed? Sorry if maybe you said that already.
Yeah, no, that's a great question. So one thing I want to emphasize with the photometry is that we are not refitting the orbits. So these are picking the best one between what the deconfuser has already fit. But in terms of what it can pick out, what we've noticed is that the most common features of the ones that it struggles with are where you have planet detections that are very near each other on sky. So everything we've simulated, the planets are at least 0.3 AU separated in their systems, but obviously depending on the system inclination, they can appear relatively close to each other on the sky. And due to either the kind of like low photon rates that you're receiving or the very similar phase angles, it starts to struggle a bit more there.
Oh yeah, cool, thanks.
All right, Jake, you have a question. Okay.
Hi, Sammy. Great talk. Have you thought about adding like RVs into your model fits or into the deconfuser to kind of add, help deconfuse things?
Yeah, that's a great question. We have like a laundry list of items that we could add to the deconfuser, honestly. Yeah, so I think that having RV priors would help you constrain the orbits quite a bit. And so it's kind of on the list, but low priority since we do have other orbit fitting tools that are able to incorporate those.
All right, great. And with that, thanks, Sammy, for a great talk. We'll transition to our next